Here's the answers to the practice quiz on predicting products of different types of reactions. There were 5 different reactions, and each had a little video so you could watch the reaction and kind of see the changes that occur. And then we're going to answer some questions about the equations. For example, number 1 was a combination or synthesis reaction between magnesium metal and oxygen gas. I want the proper balanced equation. So first, magnesium metal is just Mg. It's not diatomic, but oxygen gas is. So when oxygen is all by himself, he's got to be O2. So I can tell you right now that this first choice is not correct. The oxygen's got to be diatomic. Then I'm going to join the element symbols. Magnesium plus oxygen forms magnesium oxide. And when I join the symbols, I got to check the charges anytime I make a new product. So my magnesium is +2. My oxygen is in the group that's -2. This thing is neutral. It should be MgO, not this last one. And so the way to think about these equations is not like Mg plus O2 makes MgO2. It's magnesium plus oxygen makes magnesium oxide. And then I have to check the formula of magnesium oxide. Now I get that I've got to have 2 oxygen on both sides, and so we balance by adding the coefficients. So both of the choices in the middle are balanced. But if I think about the phases, aqueous means that something is dissolved in water. And the final product was like an ashy white, kind of ashy gray solid. I didn't have evidence that anything was dissolved in water. There was no water at all in this equation or this reaction. The second one was a decomposition and a combustion where we had to add energy from a little burner in order to decompose some potassium chlorate. When you want to break bonds, you have to add energy. Potassium chlorate looks like this, O3. And we added energy to form potassium chloride and oxygen. Now it's not balanced, I get it. But the energy was being added to split off the oxygen. I wanted to break that bond and separate the oxygen from the potassium and chlorine. The oxygen is bonded, and that means that there's electrons that are shared or transferred, and that forms something that's stable, where everybody has a full octet in a bond. Bonding is a good thing. So if you want to come around and break a bond, then you must add energy. Adding energy means it's endothermic. Energy in, like endothermic. I have to add energy to break bonds. I mean, think about like ions that are oppositely charged and very much attracted to each other. If you want to separate them, you gotta add energy. Now the opposite would be true of a combination or a synthesis. When I'm forming bonds, energy is released, because that's when electrons are shared or transferred so that I'm obtaining that full outer shell. I'm forming something that's more stable than it was originally. More stable means lower energy. So energy is released when bonds form. Energy is also released in a combustion. In a combustion, something is burning. So you should have evidence that energy is being released in the form of heat or light. So the decomposition was endothermic. I had to add heat from a little burner. But the combustion was definitely exothermic. Energy was produced or released. There was another combustion with methane gas. What is wrong with this equation? So we've got this proposed balanced equation. Methane is CH4. Combustion means that it's burning in the presence of oxygen, which is O2. And the products are always carbon dioxide and water. So the formulas look fine. If I check to see if it's balanced, 1 carbon, 4 hydrogen. Nope, the oxygen's not balanced. Here there's 2. Here there's another 2. So if I want 4 oxygen, I really need to put that coefficient in front of the O2. The water was in the gas phase. Because combustions are exothermic, energy is released. And that energy release will often vaporize the water. No, 4O would be 4 atoms of oxygen, but oxygen gas is diatomic. And it's not really a replacement. It's not that oxygen is replacing the hydrogen. This is kind of a special reaction that always forms carbon dioxide and water. Then we went on to our replacements. So we had a single replacement between aluminum wire and lead nitrate solution. The reaction worked, and so we can write the balanced equation. Aluminum should just be Al. It's not diatomic. But the lead nitrate, I might want to check this formula. Lead 2 means that its charge is 2. Nitrate with the ATE ending is the polyatomic. The polyatomic nitrate is -1. So polyatomics will be given to you. They're on that chart on page 98 in your book. But the key is that I have to watch the ending. ATE is nitrate. And from here, I just kind of either crisscross the charges or balance it. To make this neutral, I'm going to need 2 nitrates. This third one down is not lead nitrate. That might be nitride. Nitride with the IDE ending is just regular nitrogen, and its charge is -3. And so it's a legit formula for lead 2 nitride, but that's not what we got. Okay, so the other ones have the right formula for the lead nitrate. Then we're going to do the replacement. So the aluminum is charged +3. So because it's positive, it wants to switch with the other positive ion, lead. So my products then should be lead solid, it's a metal, solid, and then aluminum will come in with nitrate. So again, not nitride, nitrate. But when I make a new product, I've got to check the charges. So if now I have aluminum with nitrate, well, nitrate is still -1, but it's bonded to something that's +3. So my formula is going to be a little different. Not 2 nitrates, 3 nitrates, because I bonded nitrate with something new, and its charge was a little different. All right, so it's got to be one of the first 2. And it looks like the first 2 are both balanced properly. Both sides have 2 aluminum, 3 lead, and 6 nitrate. So I have all the right formulas, they're both balanced, but there really should only be 1 solid. The only solid was the lead. The aluminum nitrate, that guy should be a solution. It should be aqueous. And so if you're not sure of a phase, check the solubility chart. It'll be given to you in the test. It's on page 246 in the book. That solubility chart will always be provided for you. It helps you to decide between solid and aqueous. Is this going to dissolve in water, or will it be a solid? And if it wasn't sure, just check the chart. Nitrates should all be soluble, which means aqueous. That's a good one. I like that. With a single replacement, then, the other rule was that your single element needed to be more reactive than the element it replaces. So we tried this with aluminum and copper. And obviously the aluminum was able to switch with lead and form solid lead. Well, the rule is that your single element needs to be more reactive than the one it replaces. And so, yeah, aluminum is more reactive than lead, so this works. The other one we tried, though, was copper. And that one did not work because copper is less reactive than lead. So no reaction. Now, we could have used any other element more reactive than lead. So iron, zinc, aluminum, magnesium, and so on. They would have all worked, and we would have formed the lead metal. But not silver. Silver, again, is less reactive than lead. But I could have used any of the other elements. And finally, my double replacement. We had a double replacement with potassium iodide and lead nitrate. I'll switch these and make them iodide, I suppose. On your solubility chart, they don't have iodides, which is fine. Iodides and chlorides follow a lot of the same rules. All halogens form a lot of the same types of compounds. I'll switch this to Ki. There we go. So this is the combination that I ended up picking just because I had a lot of extra potassium iodide to get rid of. I could have used potassium chloride, but I think the precipitate is a little bit brighter when it's the lead iodide instead of the lead chloride. So bright yellow, isn't it? So here we just want to know the identity of the yellow precipitate. I didn't really have to write the equation. I kind of started to sketch it out. I didn't balance it yet. But I wrote the formula for the potassium iodide and the lead nitrate. So I recognize then that there's two compounds. This is my double replacement. I switched the positive ions. So potassium switches with lead. And you don't have to check any reactivity chart. Double replacements work as long as your two reactants will dissolve in water. They usually don't work so great when they're solids, but in solution, the ions dissociate and separate from one another, and then they're willing to bond with somebody new. All right, so I switched the lead and the potassium, and I did kind of write my formulas on the product side. I should have had lead with iodine, and even the iodine is -1, -1. And then I had potassium with nitrate. Really, I just wanted to know what the products would have been. And so when they asked me for the identity of the yellow precipitate, I know for sure it's not potassium iodide. That's a reactant. Same thing with the lead nitrate. It can't be those two. It says, what is the identity of the yellow precipitate? Well, that was something that was produced. So it's got to either be the lead iodide or the potassium nitrate. From there, I can just check this solubility chart. So lead's probably not on the chart. It doesn't have every ion, but I bet one of the ions in your compound is on the chart. And again, here there's a little note that says iodides follow the same rules as chlorides. Most halogens follow the same rules. So chloride salts or iodides are soluble. There are a few exceptions. Oh, bummer. Lead is one of them. So most chlorides dissolve, most iodides dissolve, but not silver, mercury, and lead. That's my precipitate, the lead iodide. Now, potassium is an alkali metal. Alkali metals are soluble with just a few lithium exceptions. So that potassium nitrate is soluble, meaning aqueous. Same thing, nitrates are on here too. Nitrate salts are soluble with few exceptions. So for sure, that potassium nitrate will dissolve and be aqueous, but the insoluble product would be the lead iodide. Good stuff. There's that solubility chart in action. And then the last one would have been the final balanced equation. So I got my formulas correct. I checked all my charges. They're balanced. There should be 1 lead, 2 nitrate, 2 potassium, 2 chlorine. And I got the right phases. that my reactants were solutions, so they were aqueous. And then on the product side, there should be one solid, just the lead chloride. And my other solid was, or my other product was the aqueous solution of potassium nitrate.